Hello, my name is Souad Lagmiri. I'm from the University of Paris-Cité. Our research focuses on the distribution of air pollutants due to urban forms, a case study in Cergy-Pontoise. Among the Sustainable Development Goals is to continuously monitor air quality. To this end, many control stations have been installed in the city. Usually, an official network covers, on average, about 100,000 people in cities in developed countries. However, this distribution is insufficient to obtain precise information on the spatial distribution of emissions. Since the discharges of primary pollutants are not homogeneous throughout the urban environment, no pollution reduction measure can be effectively conducted without prior research on the spatio-temporal variability of pollution. Unfortunately, only one control station is installed in Cergy-Pontoise, our study area, and therefore a very low level of spatial resolution. This appears to be a significant limit since there is not a lot of data available to study pollution. Overcoming this handicap is my goal. The points cited here develop my objective a little. What should be remembered is that I will introduce a network of sensors, draw up an inventory, and analyze the factors acting on variability. For once, our work is based first on installing a network made up of 16 measuring stations that monitor the concentrations of nitrogen dioxide via a chemical component and an optical component of PM10. Each station also combines a component to detect temperature, humidity, and pressure. As you can see in the photo, the sensors are designed to operate on a power supply. If you ask me a question about calibration, I will tell you that the sensors are calibrated with reference analyzers, which themselves are calibrated annually according to the ISO 17025 standard. Overall, our sensors have a fairly high degree of performance. Performance is shown in this table. So I briefly present to you the installation sites. I have a whole table that summarizes the characteristics of each site, but I did not want to show you a table that we will not have time to read in 12 minutes. I can assure you that we focus more on sites with architectural and functional differences. Of course, all the interest in this installation rests on the fact that one could thus obtain results that would cover a significant number of urban forms. What is the principle of statistical treatment? Already the study period goes from April to June, and the measurements are taken every minute and transmitted by Wi-Fi. We have detected a large number of incomplete data linked to a break in the power supply or the cellular communication between the automatic station and the web server. This data was estimated by the average of the corresponding hour. Once the time series are complete, we carried out a pre-processing based on the calculation of the median value of each hour to eliminate the very low values and the instantaneous peak related to the passage of vehicles. Under the SPSS software, we grouped the sites presenting a similar pollution rhythm according to the ascending hierarchical classification technique. The results of this grouping are therefore used as input in the Kolmogorov-Smirnov test for the verification of the statistical normality of the distribution, and then the Kruskal-Wallis test to inspect the spatial configuration. The GIS is used to map a display of pollution. Here, I will present to you what we obtained as results. Rather than focus on a manual grouping of sites that have similar architectural and functional characteristics, I therefore chose the objective grouping of sites. Here is code for each size. The process resulted in the identification of 5 groups of nitrogen dioxide and 4 groups of PM10. If you notice here, the composition of the groups by category of the site shows that PM10 and nitrogen dioxide do not essentially come from the same source, or the conditions of dispersion act differently. Then I launched the Smirnov test. The results of this test are reported in the table. They show for all the pollutants of a p-value below the significance level at 0.05 and a maximum significant difference between the measured and Gaussian values. This means that the concentrations in the different groups do not follow a normal distribution. In this case, I favored the independent Kruskal-Wallis non-parametric test to assess spatial heterogeneity. All spatial series were found to have statistically significant variability with a p-value lower than 0.05. This result could most likely be explained by the distribution of emission sources and by the particular topography of the sampling sites. Analysis of the Bloch plots from the Kruskal-Wallis test isolates three concentration zones for nitrogen dioxide. High, group D4, moderate, group D2, D3, and low, group D1. And then, in a complementary aspect, we issued a spatial pattern of pollution to verify the differences between the sites. The disadvantage is that this type of map is based only on an average value without taking into account the variations that may exist over time. What I can tell you from this is that the analysis of topographic properties has allowed us to identify two main factors affecting air quality: the sky quality, the flow, and the speed of traffic. Regarding the PM10, we also obtained differences between all the groups. It could be wise to specify that the difference is not obvious in the box plots, but from the map, we can still see that the concentrations are not homogeneous. High concentrations are noted in sites under construction and vegetated sites. In fact, in these sites, the pollution is mainly due to the strong pollution activity, which increases the concentrations of PM10. In addition, even if car traffic is less there, each time a car passes, it can easily raise dust from the floors. The lowest concentration levels are found in these sites, and these sites with a high traffic flow. In fact, here there's a barrier hedge and a wall barrier established between the motorway and the houses, which prevent the spread of PM10 towards these sites. We have shown above that the A15 motorway is the most polluted in nitrogen dioxide. We can then conclude that the headage line, which is a porous barrier, is only effective in the case of particulate pollution. Weekly and daily cycle of pollutants. We have found that during the morning and evening rush hours, that nitrogen dioxide concentrations are the highest because the traffic is active. In the middle of the day, the concentrations drop due to decrease in emissions compared to peak hours, combined with greater turbulence in the boundary layer due to solar heating and chemical reactions. After the evening rush hour, concentrations slowly decrease until the early morning hours. Overall, they remain higher than during the day due to a weak lower boundary layer. This time profile is observed from Monday to Friday. During the weekend, the morning peak is reduced on Saturday and absent on Sunday. Light nitrogen dioxide daily amplitudes of PM10 are well marked, showing that the concentrations are also influenced by environmental factors. As you can see here, the daily cycle shows a high morning peak. This may be related in addition to transport to the pollen rate, which is particularly high in the morning. The morning peak can also be justified by the transition phase between the nocturnal and convective layer, which is rather rapid after sunrise. Unlike the transition at the end of the day, which is slow. PM10 trapped overnight is quickly re-injected to the surface in the morning. Unlike nitrogen dioxide, PM10 concentrations are higher during the day due to turbulence and pollen activity. What I have just presented is an overview of an air quality from April to early June. The interpretation of the results lead us to grant relative confidence and caution as to the impact of the different time scales, because the spatial distribution can be variable according to the types of weather. So if we look closely at the impact of weather situations, we will see, for example, for nitrogen dioxide, we will see that the concentrations of nitrogen dioxide are high in stable weather. Indeed, a clear sky with a low wind speed governs the concentrations of atmospheric pollutants by reducing their dilution after emission. Distributed weather pattern increasing dispersion and reducing concentrations for all monitoring stations. Compared to the WHO standard, nitrogen dioxide concentrations are much higher than the standard value in all meteorological situations. The overshoot is significantly linked to the emission of nitrogen dioxide gases by vehicles and is favored by stable weather. The latter, therefore, presents a higher risk of exposure because the nitrogen dioxide gas, often emitted near the ground, remains trapped in the lower layers of the atmosphere. Unlike gaseous pollution, particulate pollution, PM10, is higher in distributed weather. More precisely, it is the concentration above the median that becomes stronger compared to the stable time. Quite simply because at a greater speed of wind, sedimentary pollutants on the ground can be lifted, creating new dust pollution. The concentrations of PM10 in the third and fourth quartiles indicate that the majority of the stations only record less than 25% of the values, exceeding the WHO standard. For all situations combined, there is only one exception in these sites, A1 and A14, where the percentage of excess reaches 35% of the values. The box plots also show that some stations never exceed the standard, even in distributed weather. Sites A3, A8, A11, and A16. In conclusion, I would like to tell you that the study allowed us to understand how urban forms impact pollution, yet we were able to identify that there is a small difference between weekday and weekend concentrations, suggesting a small impact on the weekly cycle of human activities. Moreover, the daily cycle shows a bimodal cycle. Today, we are analysing the impact of the relief, which will complete the study. Thank you for your attention.